Okay, now we're switching back to Euclid. I want to continue on with this book for a few more problems and theorems. I'm not sure exactly how far, but I don't think we've done enough yet to really get a feel for what sorts of conclusions and theorems we can come up with given what we've started with. We're just starting to get going. We can draw perpendiculars, and that's a major advance. We finished the last time here on problem 11, where we were, from a given point on a straight line, able to construct a perpendicular, in fact a perpendicular bisector of a line constructed from the point. So we constructed a line that had equal sides in that case, and so therefore we were able to make an isosceles, and we were also able to by problem 8, infer that these two angles had to be equal. Problem 8 says, okay, is that right? Problem 8? Equal angles, okay, well it's just a weirdo. How does this relate to problem 8? These angles are equal. Oh, therefore all angles are equal in the two triangles. Yeah. Yellow common. If you have common sides, then you have common angles. If it's the same triangle identically, and this side is the same as this side, right? And this side is the same as this side by virtue of construction, and so therefore these two angles are equal, and then by definition yellow is perpendicular to the constructed line. Here we're sort of doing it in reverse, starting with a point outside of a line, an indefinite straight line, from a given point indicated by this. We are to draw a line perpendicular to the given indefinite line. So we're taking this as a center, okay, at one side of the line, and any distance. Okay, at one side, and any distance capable of extending to the other side, describe a circle. So if we take this as a center point and extend to some distance beyond the given line, let's say here, and then describe a circle, that circle will, by necessity, cross the line at 2 points. And the 2 points where it crosses the line will have this point and this line as a bisector. This will be the center. This will be the center of these 2 points in this direction, in the direction perpendicular to the line. that right? Anyway, let's see. First, set this up to draw such a line. This line is exactly the width of this field, it turns out. And now I want to take what we are given is a point. I'll label P, just to show what we're given, and what our task is to draw from P a perpendicular to L, let's say. If we now draw a circle, I could use a pi, or I could use a full circle. Take this point and extend to any distance beyond the line. Whatever, doesn't matter. It may or may not indicate a radius. I haven't. And now, actually, I want blue, I think. This color. To the intersection points of the circle and the line, two of which there are two, I'm going to draw two equal length lines. One, equal length because they have to be by definition one radius distance away from P. These lines are equal length. Okay, we've done that. And I've also, in doing so, created a line segment, a finite segment of the line. And by problem 10, we can bisect that line. Look at these here, let's say. First, maybe I can just draw it. Not likely. I can draw it. Oh, I can use my tool. If I knew the length of that line. I don't know how long it is. I drew it in a kind of arbitrary way. Shorter than that. Doesn't matter. 50. That's it. Almost. Okay, that's almost ready. Okay, now this line we can bisect. According to problem 10, and the one side white with one side white and one side yellow. This, thank God, was an even number, a number I could divide into one white and one yellow. It's not exact. Now it's bisected, and we can now draw a red line from the intersection of the two segments. And again, make cheat. Not red. It's going to be longer than 25, maybe 30 less. Oh, no, it's less than 25. Looks like. Too short. How about 25 exactly? I'm always drawing equilateral or something. Almost too long. There we go. Now by construction, that red line that is true, even without cheating, would be perpendicular. It would be a perpendicular bisector of a constructed line from an indefinite line. Okay. And y, black is equal to yellow by construction. True. Red is common to both that and the blue sides. True enough. Common. And therefore, these two angles must be the same. Trying to indicate the symmetry of the situation. I can use my pi. I can use my pi. And make a pink thing and another pi. Which is purple, let's say. These two angles being identical by construction, and therefore red is perpendicular to these two, because these two have to be right angles because they're equal, and this is a straight line and this is a straight line intersecting a straight line by definition. So that's done. Next is a theorem. When a straight line, so I'll do this one more. When a straight line, yellow, standing upon another straight line, red, okay, go back. Straight line, red, you ready? Make it a bit longer. Let's say 60. And let's create a yellow line at an angle. 90 straight up and down. What does this picture look like? His picture looks more like about 60 odd. Quite shorter. There we go. When a straight line yellow standing upon another line red makes angles with it, they are either two right angles, so disregarding this red, if we take these angles, pi, as before, what he's talking about are this angle and this angle. Okay. These are either two right angles or together equal to two right angles. So we want to, sorry. Okay, so either these are each of them to the right angle in the last case, as in the last case, or the sum of them, if taken to be a type of quantity, will be equal to 2 right angles. That's the theorem. Does it have a number? What was the number of our last theorem? I don't know if I can get it right. Theorem 6, it appears. I know I didn't. Gotta get rid of that. Theorem 6. Oh, geez. Theorem 6. Okay, so either the pink and purple are right angles, or their sum is a right angle. Okay. If yellow be perpendicular to red, that's this one, then then by definition the two would be equal, right? So that's the trivial case. So let us assume that's not true. Let us assume they're not, yellow is not perpendicular to red. From the last problem, we can draw, or from, sorry, not the last problem, but from this problem of 11, right? Well, actually, no. From these together, we can draw a perpendicular line to this point, at the point of intersection. How would we do that? Well, there are many ways, but one way would be to take a point here and construct the same line like this, and the perpendicular bisector would be at the center, would be central with respect to the point, just as the last problem. So we'll draw a perpendicular. We may draw a perpendicular white, same as his black. At any point we wish, we can select a point. It's too big. There we go. We can draw a perpendicular line like that. We would simply choose a point beyond the line, draw a circle. The circle forms a line segment which we may bisect and draw perpendicular from the center point, which by definition is this point. On the other hand, how did I get this point? Not sure. In any event, one can certainly figure out a way. Oh, 11 it says. Okay, so this one. Right. Right, of course. That would be that we can do from any given point on any given line. We can draw a perpendicular perpendicular line, and here it is. In which case, we end up cutting this angle into two different angles, one of which is known to be a right angle. So we get rid of that, fix that problem, and draw two pies, different colors. One of which is known to be a right angle from the last problem. Okay? Now, we know that the sum of these two angles, in my case, orange plus this sum, is equal to two right angles. It's raining now, but I have to think you can still hear me, and I don't need to raise my voice. Can't hear myself, though. So by construction, yellow and this sum are equal to the sum of two right angles. This two right angles. And this is, by definition, sum of these two. I'm saying this one, okay, something like that. The text is different. Color-wise, I keep having to switch colors, and I don't need to. The pies should have their color, and the text should have its own color. And save me typing. That'll be my next feature. The big feature I'm having trouble with is the nesting of those specially formatted strings, like the square root and a vector and so on. I'm not sure where to start. Okay, now what we can, so therefore, according to axiom 2, so what's axiom 2? This is actually, I remember taking note of this because this one doesn't follow by axiom. If equals to be added to equals sums will be equal. That much is true. That like it's an axiom, but by definition true. But what he and everybody else in the world has failed to realize is that this theorem, the writing down of a sum, an open sum like this, has not been stated as an axiom That is, the associative property hasn't been stated explicitly when it comes to adding angles. This part, as far as axiom 2 goes, number 2, adding equals to equals on this side, switch side first, this plus this sum isn't going to look like great, but okay, should be equal to 2 right angles. Okay, what he wants to write is this, I don't have enough room, plus then what would have to be written first is this in brackets, because we haven't a law of association, an associative law for addition of angles. That needs to be added to the axioms, and one could do that, or one could say that these are quantities as numbers, and therefore the associative principle applies. But we just accepted that he hasn't taken that. He is taken as given the law of the principle of association for addition of angles. Okay, so that's one very obvious mistake in the book. And probably most writing at the time, mathematical writing, took this step, which I could label star or something. This star step for granted, but actually there are constructs that can be developed that do not obey this principle. Subtraction was one example. If this were a minus sign, right, we couldn't do the same thing, right? If this equals this minus this, that's not the same as this minus this. It turns out, right? Just by doing it. One gives 0 and one gives something that's, oh, actually, no, they do come out to 0 in this case. No, they don't. This minus this is not 0. This is smaller than this. So subtraction wouldn't follow if it were subtraction. But anyway, and we also know that that's equal to 2 right angles by construction, right? We also have this equals that. And who knows how much I gotta be just slightly above. Whoops. I gotta be in the middle. There we go. It's gonna go one way or the other. It would be random. But anyway, let's take that as a straight line. I could turn it into a straight line. Like that. Okay. So we know that this is two right angles. So we have two right angles equals this plus this. So we've proven the theorem. These are equal. So the angles, before this was a different color. This color, I think. This sum, which is a single angle, is one of the angles created by yellow intersecting red, and so therefore the theorem is proved. Okay, so that's it for this one. And again, I want to just make clear that there's an assumption that's being made here that is not allowed to be made. It should be made explicit. There ought to be, in addition to the other axioms, the associative axiom for addition of angles. Okay, whether or not it's the associative principle applies to lengths is also not given, and it may or may not be true. Okay? Depends on how we add lengths. A method has been given for subtracting lengths at this point. So far, I think that was problem 2, 3. Here we have a method for subtracting a length from a length. It's a type of subtraction, right? We take a long line and a short line and produce one of the shorter segments from the longer. That's a type of subtraction. So in a sense, if we inverted this procedure, we'd have a type of addition. If it's associative or not cannot be proven by any means. It has to be stated as an axiom. The next theorem is getting closer to, I think, what one of the next important fundamental theorems of geometry is, you can see what's happening here, right? Here we have blue and black, okay, a straight line, blue, black, an arbitrary line like this yellow, creating these two angles which add up to a right angle. And now what he wishes to show this is a contradiction, right? Not the continuation of yep. Okay, and now he's showing that if we take another yellow line well, the same point, make adjacent angles such as so, two right angles. The lines lie, oh, I see. He's done. He's going. This is the only if part of this. Right? Here we've taken a line, cutting a straight line red, and that produces something that adds up to two right angles. This is going the other way around. Suppose a line cuts two line segments or rays, starting from the same point, and the angles add up to two right angles. He wishes to prove that therefore these must lie in the same straight line, and that proof is given by constructing a contradiction, and therefore in the end blue and black lie in the same straight line. Okay, we'll get to that another day.